Welcome to another live for the Assumptions of Physics program. Today we are going to have a student that has been working with me for the past 3 months present. And this is really the idea of trying to make this a more open research where people can contribute to the project, come here, present, and then we can discuss what things needs to be done and so on. So the problem that we're going to discuss today, it's essentially studying how uncertainty propagates in classical mechanics. So as part of the reverse physics, we have seen that Hamilton mechanics is essentially equivalent to saying that the uncertainty in each degree of freedom as it moves is preserved. But it's preserved in the sense that if you start with uncertainty 1 degree of freedom, when you evolve, there is going to be another degree of freedom with the same uncertainty, which is not the same degree of freedom that you had before. So if you have 1 degree of freedom, just 1 degree of freedom, things are easy. If you have multiple degrees of freedom, there is this sort of movement across degrees of freedom. So the idea instead is to characterize the same evolution on what happens in a fixed degree of freedom. So we want to say we have these n degrees of freedom and understand how the uncertainty propagates across them. And the way that we want to do it is essentially studying the symplectic group, which is the sort of the group of transformation of linear transformations that Hamilton mechanics allows, and then try to understand what happens to the uncertainty in the covariance matrix. And what we think it should happen is that we should be able to see essentially if we break up the covariance matrix into a block matrix, we should be able to see uncertainty sort of propagates across these block matrices that represents the variance within a single degree of freedoms and the covariance across. And so hopefully what we try to see is that there may be a way to simplify this understanding of the uncertainty in terms of these determinants of the blocks, hopefully. And in general, we would like to hope to show that essentially Hamiltonian mechanics is exactly the preservation of the lower bound on the entropy in each degree of freedom. So, for example, if you start with an uncertainty that has 0 entropy in each degree of freedom, then as you evolve, you can't increase the uncertainty on one side while decreasing the uncertainty on the other degrees of freedom. So that you can always sort of trade uncertainty from one degree of freedom or the other. You can create correlation, thus creating more uncertainty in each degree of freedom, but you can never do this trading. And so the real final goal would be sort of have an equivalent characterization of Hamiltonian mechanics in terms of how the uncertainty move in a fixed set of degrees of freedom. And so the way they want to do it is by studying the symplectic group, trying to find a comfortable characterization in terms of the generators of the group, and then try to understand how these generators act on the covariance matrix, and hopefully we get nice expressions. So I leave it to Najim to present himself and to tell us a little bit of what he has been working on.
So, hello everyone. I don't know if it's okay for the live. So, as Gabriele was saying, for my degree this year, I chose to contact Gabriele to work with him on the project. And he asked me if we can do a collab about those kind of questions for the Simplicity group. So, I'm going to share my screen. I did a little presentation. It's the one for finishing my degree actually, so it's maybe too professional or too academic, but we are going to discuss on it anyway. So, as Gabriele was saying, we want to study this group because it is the one that can represent how the Poisson bracket acts on the phase space. And one thing that we noticed is that the simplicity group is one kind of Lie group. And because at the end of the day, we want to describe all of this group to show if the covariance matrix after auto calculation will evolve in a way that preserves all the things about each degrees of freedom. And to do so, what we did is that we went to see how the Lie algebra associated with the Lie group works. Because if we want to generate a Lie group, it is better to go to the Lie algebra. Technically, for a lot of cases, the number of elements is really small. And so for the Lie algebra, we wanted to define those elements and then how those elements can react with vectors of the phase space, and if we can recover the Hamiltonian mechanics due to them. To do so, we first described how the symplectic form omega is represented in the form of a matrix. And then we can have a condition on the matrices J, the element of the Lie algebra SP2N, and this symplectic form, the relation is this one. And so if we want to describe by block an element of the Lie algebra, we have some condition on the blocks. At the end, we see that the one element of the Lie algebra is of that form, and the dimension of the Lie algebra is for n degrees of freedom, n times 2n plus 1. Our goal is to, when we want to work on the shapes of all those elements of the Lie algebra, is to find at the end of the day the same dimension so that we can ensure that we described all of the Lie algebra. And to do so, we wanted to go from an arbitrary element and to ask ourselves this question: how can we describe, in terms of matrices, the a quadratic element of an Hamiltonian? And to do so, we want to define a symmetric tensor called little h. With this definition, we can see from the definition of the element of the Lie algebra that this matrix is symmetric. So we can afterward define an Hamiltonian called capital H. It is defined with this matrix when we apply some vector xi of the phase space. And then if we want to evaluate how one vector of the phase space can evolve with the Hamiltonian equation, we find that the time evolution of a vector space of the phase space evolve with this exponential map. And this exponential map with the element J, an element of the Lie algebra, is the exact definition of an element of the Lie group associated with this Lie algebra. So the flow exponential of t times J is recovering actually all the element of the Lie group that we want to study for the Crochet-Poisson and the evolution of the covariance matrix.
So let me discuss a little bit so that it's a little bit clear. So if you can see that the Hamiltonian there is just quadratic, so it's gonna get all the term PP, QP of all the degrees of freedom. So, and it is quadratic because we are studying essentially all the linear evolutions. And so if the Hamiltonian is quadratic, you take one derivative of Hamiltonian, that is going to be a linear function. And so the Hamilton's equation in the last line, that CA equals omega AB partial h, that partial h now will only have one xi, and so the JAC is just a matrix, so that's just a linear system, right? And so the link is between the quadratic Hamiltonian to the J, which is the generator, meaning the linear a transformation from the state to the derivative, and uh, and then once you have a linear system, then the solution is just an exponential, right? So that's basically the building blocks.
Thank you. And then that was only one side of the equivalence that I wanted to show. I find that if we want to go the other way, so beginning from an arbitrary Hamiltonian described as such, we can see that, oh, sorry, this Hamiltonian is symmetric. And then if we want to derive the Hamilton's equation, we get, sorry, we get this expression, a matrix actually, because we have an A here, a C there, and the B's are just saturated. And if we define this product of two terms as a matrix J, we can check that we end up with the same definition of the element of the Lie algebra. So I proved the two ways. So coming from an Hamiltonian to a generator or element of the Lie algebra, and in the other way. So at the end of the day, we can define a dictionary between terms of quadratic Hamiltonians and the Lie algebra sp2n of R. We tried to do so with 1 degree of freedom. Thanks to our formula, we have three elements, and it's exactly representing the QP term, the P squared, and the Q squared terms with those three matrix. And we see that those kind of transformation just represent transformation, physical transformation that can act on the phase space. One thing is more the mathematical side, but for 1 degree of freedom, sorry, the symplectic algebra is isomorphic to SL2. So, and then
You don't have
afterwards,
the pictures for the flows?
I don't have them on the slides. I may
Okay.
be going to take them after if we
Yeah,
if I can.
it was just to give a sense. So
Okay.
maybe you can describe them a little bit, what happens.
Okay. So for squeezing, we get that we will have one variable, maybe the Q variable, that will be shortened, for example, and the P variable that is going to be enlarged, or the opposite, if we change the sign. For rotation, we have that the uncertainty, for example, for one variable can just rotate in the phase space. And for the boost is just an hyperbolic rotation. So we have the same aspect in a Minkowski diagram, for example, but here we have P and Q as the variables. Maybe I'm going to show them when I finish, so it will be more clear for
Yeah,
everyone.
just to give a general sense of what.
May I continue? I don't know
Yeah.
if.
Go ahead, go ahead.
So then we wanted to describe how those kind of evolution occurs when we have more than 1 degree of freedom. And to do so, we have to understand that because we have 2 degrees of freedom, we have four variables, Q1, P1, Q2, and P2. And the quadratic terms are then those given by uh, the same degrees of freedom. So qi, pi, and then the qi squared and pi squared, and then the cross terms, sorry. So when we mixed some variables of 1 degree of freedom with variables of the other one. And when we count the number of transformation or element, technically, we get 10 elements. And it's check the formula of the dimension of the Lie algebra associated with it. So we wanted to describe it as two families of generators, one within a degrees of freedom. So I wrote particle. You told me don't to you told me not to do so, but I forgot. Sorry. But the intrasector generator, those are the ones that are acting only on 1 degrees of freedom, and then the intersector, when the generator mixes up the 2 degrees of freedom. We have the shape of them. So we called squeezing, rotation, and boost just the equivalent of our three element of sp2, the three we saw before. But then we have the same at this block, the fourth one, for the second sector. So if we have two particles, the first sector is only the dynamics for the first degrees of freedom. The fourth one, the bottom right one, would be for the second particle. And when the two other blocks on the anti-diagonal are not zero, means that we have some kind of pair evolution. We are going to see how those show themselves. When we wanted to do so, we find ourselves with some not really nice expression. So we wanted to see if that by changing the variables or how we can write them, sorry, we can maybe get a nicer picture of those matrices, sorry. And so for the rotation and the boost appearing when we mixes the two degrees of freedom, we get that we have those kind of matrix. So we get also, sorry, the Hamiltonian linked to those generators. And then we can see that for the, so a little bit of terminology here, sorry. The R and the B stands for rotation and boost, and the S or M stand for separated when we have dynamics separated from one degrees of freedom to the other, sorry, from one kind of variables to the other, and when those are mixed. And we see that within this change of variables, we get that the separated like generator only acts on the diagonal when we have the block matrix. And for our mixed one, we see that the non-zero block are on the anti-diagonal. So at the end of the day, when we count, we get exactly 10 generators, so the number of generators for this Lie algebra. We wanted to generalize a little bit and see if we can extend it for n degrees of freedom. And to do so, the only assumption that we took is that we know for sure that an interaction, a correlation, only occurs between two particles within a pair of particles or degrees of freedom. So we wanted to describe our generator S, R, and B for the intra sector and RS, RM, BS, and BM for pairs of degrees of freedom. And when we count for n degrees of freedom, we get exactly n times 2n plus 1 generators, so exactly the dimension of our Lie algebra sp21 of R. So at the end, we saw that to be able to describe any kind of generator of this Lie algebra, we can just decompose the generator as a block matrix of 2 by 2 blocks, and those 2 by 2 blocks are only element of the sp2r because the sp2r only occurs like how to phrase it. The sp2r already gets all the evolution that can occurs for 1 degrees of freedom or when we have correlation between them. So at the end, that's what I've done during those months. And from that J at the end, we can recover the Lie group that we wanted to study with the covariance matrix. So that pretty much all of it. I may stop the sharing just so I can find
See,
those graphs.
let me comment on this. So
Yeah.
the typical way that the generators are sort of recovered when people look at this symplectic group, they do the decomposition instead of doing like we are trying to do in with each degrees of freedom. They sort of group all the position and all the momentum. So instead of
Yeah.
having an n by n block matrix of 2 by 2s, you have a 2 by 2 matrix of n by n. And so you
Mm.
lose, like you can't really see with those generators what's happening inside degrees of freedom, outside of degree of freedom, and you can't write sort of like we are doing a set of generators that sort of generalize, right? So for us now, all those matrices basically are always the same because they're effectively just two by two matrices. We're just adding the new indices. So if you go from 3 to 10 degrees of freedom, you're still studying that, those two by two matrices, just that you have more of them, right? And so that's what allows us to basically try to study a little bit better this in terms of a more physical, sort of to get more physical intuition of what's going on. And again, the problem is that with 2 degrees of freedom, you have a four-dimensional space, and try to understand what's happening in a four-dimensional space. It's hard. So we're trying to find ways that that things that things are more intuitive. There is a question from the chat from Julius. In the beginning, do those three parts correspond to traceless, symmetric, and antisymmetric parts? Then can we use hydrodynamical interpretation, i.e. volume expansion, shear, and vorticity?
Really?
Should you want to
I
try to
didn't.
answer or I'll answer?
You can answer because I didn't thought of that in
Okay,
any way
so
possible.
there is no volume expansion in Hamiltonian mechanics. Everything conserves the flow. So you basically in the local for the local transformation, for the linear transformation, the only thing that you're missing is the sort of the whole volume expanding or contracting, and the other ones are all the other transformations that you can have. For shear and vorticity, I think you could get shear if you combine. Let's see if I get this right. You have to combine a squeezing with a rotation, I think. No, you have to a rotation with the boost, because then what's going to happen is, for example, if you do the rotation minus the boost, the q's is going to go away, so you just have the p square, and then you're going to have the shear in q. And we are trying to get as much as possible, if we can make all these generators look like rotations and boosts, it's gonna be a lot easier, because we want to then to recover, for example, the group of just Lorentz boosts. If you do this in relativistically, right, the Lorentz boost should be one of the possible symplectic transformations. So it would be nice to be able to recover that as well. Okay, Najim, go ahead.
So that was pretty much all of it. I didn't wanted to write about the things we've done on the covariance matrix because it wasn't like too concrete to be able to show, but to discuss it would be great.
Exactly, yeah.
So the thing is that for the next part of the work, I need to show that when we want to apply some element of the Lie algebra SP to N of R uh, to a covariance matrix, we want to show that and it was Gabriele that were talking about that in the beginning. We want to show that the determinant of the covariance matrix doesn't or is in some way restricted by how we can evolve with time. We want to show that we can't have any kind of marginally rising entropy, or for some degrees of freedom, an entropy that is going to rise and for other going to stay the same. And to do so, we may face some problem, I think, but I hope that at the end we will be able to counter them. So that's pretty much all of it. I don't know if Gabriele, you want to say something about how the determinant, the thing you were telling me
So I
Wednesday.
think we should show the pictures first, right?
Yeah. Oh, okay. So the pictures for
Yeah.
the okay, okay. Just just going to okay. So it would be them, for example. I don't know. Ah, okay. The thing is that if
If
it's
if you
okay.
can just open the PDF that
Oh yeah,
we've
yeah.
also just open that. Like the fact that
Oh,
it's not fully finished, it's absolutely fine. This is not a
okay.
final work talk. It's just to show what we have been working on and the
So
progress.
it
So
would be
you can just open the overleaf if you want.
yeah, maybe this one because I have too much PDF. Okay, is it there? No. Okay. I may face some problem to show those graphs, sorry.
So why don't you stop sharing, fix
Okay.
everything, and then you start sharing?
Okay.
Because otherwise we see all your yes, exactly.
Okay, okay. No problem.
If you can't, I can also open the overleaf on my side and I can share on my side. It's not a problem.
It may be better because I don't, sorry, I don't know where the right dock is in my
Okay,
computer.
let me do that then. Okay, so I have, okay, share. There we go. So let's see if I can get some. These are always on top, so I can't see. Okay, so this we can make it smaller. Now this hides the PDF. I don't know that I can hide this. Okay, let's do it like this, and this we can make it a little bit bigger. Okay, so do you want to talk over it?
Yeah, yeah, why not? Thank you.
So I'll be
So,
your mouse. Just tell me when to scroll and
okay. Can you just go down to see the graphs?
okay,
Because it was something that wasn't in the presentation. So
there we go.
great. So as I was saying before, when we act some of the element of sp2, we get a transformation or a flow acting on the phase space. We can see for the squeeze that the q degrees of freedom is a stretch. As for the P1 is going to be contracted, and if we change the sign, it would be the opposite. For the rotation element, so the second one, we get a rotation of the phase space. So if we get some uncertainty on the phase space, we would get that the the yeah, the uncertainty of P is going to be rotated to be the one for Q, and the one for Q is going to be changed to be the one for P. So it's going to change that way. And if we have, sorry, the hyperbolic rotation or the boost, we can see that we have some kind of diagonal here. The the P plus Q1 is going inside from the outside to the zero. And for the other one, the other diagonal, we can see that it's going to be from the inside to the outside. I don't, and you may help me for that, Gabriele, if I don't understand it in the right way, but we could think of that as a way for the uncertainty of Q, for example, to be, I don't know how to phrase it. It's not that it's going to be bigger with time. I don't really know how to phrase it. maybe.
So yeah, what happens is that all of these three are area preserving transformation. The squeeze and the hyperbolic rotation, basically one, they have, if you think this as a linear transformation, that there is a matrix, they have equal and opposite eigenvalues. So if you would diagonalize this matrix, you would have a plus and a minus one, which of course then the product is the trace, the sum is the same, is zero. Therefore, whatever you're stretching on one side, you're actually shrinking on the other side. So these are volume preserving. Like the other thing that you can see that I think this picture shows it perfectly is that you have these essentially commutation relationship, the Lie algebra of the bracket. And if you understand what this algebra means, this basically is telling you how what happens to J1 once you do a transformation generated by J2. This is the same way if you want to understand the commutators in quantum mechanics and the Poisson bracket, that's how you should look at it. Like you have two generators and you want to understand how one is changed by a transformation of the other. And then you can really see that if you apply the rotation to the squeezing, well, you are rotating in this way, right? So this axis becomes this diagonal, and this axis becomes this other diagonal. So really this is just this rotated. So it's really J1. If we're acting on J2, we get J3, and then there's going to be a constant, so on. Right? So these are again one of the things that I like is to not just have the math, but actually see and understanding what those things are, and the pictures help with that intuition. Of course, doing the same thing for the pairs of degree of freedom, which is four-dimensional, it's the things that I like to get to, and it's a lot easier because we can't just make pictures or four-dimensional stuff.
So thank you. Maybe, I don't know, maybe we can show maybe the beginning of the work on the covariance matrix. It would be at the end.
Well, the other thing that I wanted to show, I don't remember the status of the document here. So these are
Yeah, those are the generator that were written in the article.
right. Yeah. So
Yeah.
you want to talk a little bit how typically people do it and how we are doing it
Oh,
differently.
okay, okay. So this article is written by some of the researcher or the doctors that are in my university, and they actually studied a little bit on the symplectic group. That is something that we are going to talk about a little bit, how in the world we didn't find any source or any kind of work about this group after, but they worked a little bit on that because they wanted to work on the quantum side of squeezed state. And a lot of time, as you were saying before, they just studied it in a way that for a phase space vector, you have at the beginning all the Q's and then all the P's. And for some article, they just generate a matrix that can do the transformation to go from one vector to the other. But thankfully for those generator, it was already done in the way that we wanted. So we find that the generator for the squeezing, the rotation, and the boost can be given by those. The thing was that it wasn't really clear how the rotation or the boost occurs. And the fact is that we wanted to be able to see when we look at the matrix that a rotation or a boost is actually happening. So what we've done is that we took some of the elements and we just rewrote them in a, in a way for us, sorry, to be able to see all the block matrix, the 2 by 2 blocks, sorry, element of the SP2 appears maybe at the top or at the bottom or at the anti-diagonal blocks for 2. for a 4 by 4 matrix, so for a 2 by 2 matrix of 2 by 2 blocks. Maybe you can just go down a
Yeah,
little.
so basically, you can see that these first four generators are equivalent to the sort of the generators that we found that are limited inside the each degree of freedom, right? Because we had this generation with a zero here, and we have the other one with the zero here. And
Yeah.
so the way that these are typically developed, it's what they're doing is similar to what other people do in the literature. Is that you do find generators, but they're not the one that sort of separate well the dynamics between from the away from the degree of freedom and across the degree of freedom. So the idea is we're trying to find generators that actually works better to get some physical intuition.
Mhm. But then even them with that picture figured out that there is only 10 generators. So the number is the same, but didn't we didn't worked it in the same way. It's,
Yeah.
I think, really more natural with our basis. We can see for which degrees of freedom this generator is acting. We can maybe show, I don't know if it's on that document, I hope so. At the end, we can see maybe that I did give an example of an element for three, I hope so. Mm, yeah, so for, yeah,
That's
great. So if we have, for example, three particles or 3 degrees of freedom, technically, because of how transparent our model is, we can, for any kind of generator J, 1, 2, 3, that we have at the bottom, we can see clearly what are the kind of elements that we used to be able to construct that matrix. For example, we can see at the top when we have the formula that the J123 is equal to alpha 1 S11. We are going to focus on this block first. This block or this term is just telling us that the first degrees of freedom is going to be squeezed by a factor alpha 1. And how can we see it clearly in the matrix? We can see the first block, so the block correlating the first degrees of freedom with the first degrees of freedom, that's the transformation occurring here is a transformation given by the squeezing element that we gave just before. When we see the second term of the expression at the top, we have alpha 2 times R22, so it's a rotation within the second degrees of freedom because the indices are 2 and 2. And so we get at the center that I maybe didn't rotate in the right way, maybe.
yes.
So yeah.
It should
But
be in the
I
diagram,
hope
yes.
I hope that the people get the idea. For for that kind of generator, we only have to see where at the top and where on the side we want to take our degrees of freedom. If we want, for example, the correlation between the first degrees of freedom with the 14th, for example, we only have to just find the part of the matrix or of the generator that represent the correlation between those two, sorry. And we can see that it's only an element of sp2. So it's either squeezing, a boost, or a rotation between those 2 degrees of freedom. And one thing that is really great is that because J is symmetric, we only have to study one triangle of the matrix. We can see that the element J at the bottom is just symmetric. Maybe the minus signs are not written in the right way, sorry, but I hope that you get the idea. For the RM13, for example, the 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 matrix product with the beta. Because Rm is an element of the sp2n that correlates the first degree of freedom, sorry, with the third, we see that the sp2 element appears 2 times it appears where the first and the third degrees of freedom uh, just cross themselves in the matrix. And the same we have for BS23. It's a product with a scalar gamma. And in the same way, we get an element of sp2 two times in the matrix. So it's really clear how an element of SP, maybe it was for here SP6 because we have three degrees of freedom, but if we have bigger matrix, we can find a way for us to really track how each degrees of freedom evolve within each degrees of freedom. We can just focus maybe on one column of 2 by 2 blocks, maybe the first one, and we can ask ourselves, okay, I'm in the first column. I'm going to look at how the first degrees of freedom is going to evolve. We can see for each 2 by 2 block how it is going to evolve with all the other degrees of freedom. So the first 2 by 2 block is within himself, and then with all the other degrees of freedom. And we can do the same exact technique for each column, so for each degrees of freedom that we get in our theory, for example. So thanks to showing that, maybe at the bottom, I get, yeah, so the covariance matrix. It's the second part of the work that I am going to do for my degree. I hope I could finish all of that before presenting it to my to my professor at the university. But the covariance matrix is a little bit harder to work on because of how the expression are evolving. I'm using Mathematica a lot of time during those last day to be able to do some project on the matrix. So to recap, we know that the covariance matrix sigma is only the matrix of all the covariances between or the variances between all variables or of all degrees of freedom within our theory. So here we have the exact model. We have the sigma Q1 Q1. So it's the variance between the Q1 variable and the Q1 variable within itself. And then after we get the covariance between the Q1 variable and the P1 variable, etc., until we get at the bottom right, the covariance between the variance, sorry, between the P variable of the nth degree of freedom and itself. And so we can show that for this kind of matrix, we can always decompose it in block matrix. And we want to study how the determinant of the sigma matrix and all the blocks, the determinant of all the blocks, sorry, are going to evolve when we apply some element of the Lie algebra, so the element J that we defined earlier. We wanted to show that when we studied how the covariance matrix evolve with time, we want to show that this time evolution is only linear, so we can define an operator that we call f, and this element f is just at the top. I don't know if you can.
Okay.
Yeah. So our insight is that for each generator j, we could end up with a relation given by time derivative of sigma AB is just a linear function capital F of j because it's depending on the generator that you are acting on the sigma matrix. And to do so, I used Mathematica to see how um, how the time derivative of the covariance matrix evolve, and if we could maybe define a linear application, a linear map to be able to go from one element to its time derivative. I don't know if for just the explication here, some people have some question. I don't know if if no, I can just
If people put them in the chat, I will,
okay.
everybody is
Because
free to interrupt us and put question in the chat. I'm managing that.
okay. So to do so, what I wanted to do is that I wanted to just study it for 2 degrees of freedom because with that, we have a little matrix, and it's better to see what is happening here. And the thing is that to show that there is a linear map between the time derivative of sigma and sigma itself, we only have to study what are the independent variables within a sigma matrix. We show that the sigma matrix is a symmetric matrix. So when we have 2 degrees of freedom, we have technically a 4 by 4 matrix. And because it is symmetric, we only have 10 independent variables. So the question is, can we find a 10 by 10 linear map such that when we take a vector that only is given by those 10 elements of the covariance matrix that are independent from one each other, can we find a 10 by 10 linear map that just takes us from one time to the other with the fact that the evolution is given, sorry, by one generator of the Lie algebra. And that's the thing that I'm really looking for right now. I'm doing it actually right now. So I hope that for the next week I'm going to be able to find some way to do so. And if not, maybe see if the generator could be written in another way so that the covariance matrix can be written in another way, maybe by a variable transformation or something like that. At the end, we only want clear and simple, simplest, simplest kind of transformation. We don't want too harsh or too difficult matrix to read because it would be too complicated. The thing is that we want to see clearly what's happening here. So that's pretty much all of it. I don't know if maybe at the bottom we wrote some. No, at the end. Yeah.
Oh, that's it. Yeah.
Yeah. So that's pretty much all of it. We we did not that much
So
technically.
yeah, we,
But
we also had like some preliminary calculation that you had done. I don't see them anymore. You probably removed them because they were
yeah,
overwhelming.
yeah,
But
they were just too big. Maybe I have it on my computer.
yeah.
I'm going to look for them. Like maybe how the, yeah, I have them. It wasn't the right. I don't know if you remember, but I didn't.
Oh, right. That there were some things that didn't. I recall
Yeah.
now because they were the
So
calculation were done. Yes, and there were some elements that didn't seem right. Yes. There is a
so
comment from Steve that says, from a strictly algebraic perspective, I'm seeing matrices over a semi-ring with other structure.
can you just maybe I'm going to take the live with me because I can't read the question. Sorry.
Ah, yeah. I need to find those tools where I can put the questions on the live stream. I have no idea how to do all those
So
things.
okay. So,
Yeah,
so
so he's basically saying that looking at this with an algebraic perspective, he says that he's seeing matrices over a semi-ring with
yeah,
other structure. But you know, I really struggle to understand things algebraically. So also
yeah,
yeah, I don't know if it's right, Steve. I can't see and understand his. I can somehow group theory like some pieces stuck in my head, others like they just don't.
it's uh it's not that easy to be able to grasp all the things that we can show with group theory, but I'm sure that when we are going to work those things to the end, it may be um, it may show us that at the beginning we could maybe wrote all the things in a clearer way and in a better way. So it's not that bad if during the process all our writings are not that clear or
Yeah,
maybe
yeah, yeah. So this is clear. So we're presenting ongoing research. So of course it's messy.
yeah,
Like we don't have the final product. So it would have been also fine to look at the calculation. But you're right. We concluded that there were some terms that were completely wrong. So that would really not help. So we're basically trying to find a way to express the determinants of these blocks. Like if there is a way with specific generators, if there is a specific way to, a specific generator that allows us to sort of see that with those expression of generation, the generators, the determinants, the evolution of the determinants sort of gets a simplified expression. That's basically what we're fishing for. And of course, we're going to have to try a bunch of different things and then find, because it's difficult to say, oh, there isn't one, but
Yeah.
my hunch is that there should be, but of course it's a hunch. We have to see if we can find it. So anyway, if
Yeah.
there are questions and people want to discuss, we basically are open. I don't. Do you have anything else to show, Najim, or
No, that was
yeah?
everything that I guess. So thank you for listening. And I don't know if some people have questions, maybe on
Yeah,
my.
we'll wait if there are questions, and typically with the chat, we have to wait till they come in because you know they have to see the video that there is a delay, then I have to put the question, and I did already the mistake in other live streams. I say, okay, there are no questions, then I end the live stream, and up a question comes after I close. So.
Mm. I may have a question myself,
Oh, then go ahead.
but it's more on the physical side, technically, and I hope that people may react with it. But when we are, when will we be able to describe how the covariance matrix evolve and how the determinant evolve and all of that? I just want to for you, if you can just explain, Gabriele, how can from those elements we can coming back to the theory of entropy that you were talking about is some of the video and the thing that you were showing me last time about the uncertainty principle for classical mechanics. Can you
Yes.
just explain to me a little bit how those pieces just are going to be part of all of that, if it's
Yeah.
going to be part of all of that, sorry. So,
So what essentially happens is if you have a distribution over 2 degrees of freedom and you put a lower bound on the entropy, that lower bound on the entropy will put a lower bound on the determinant of the covariance matrix. And so
okay.
what we want to basically show is that those lower bounds on the covariance matrices of each independent degrees of freedom, right?
Yeah.
Like that bound essentially keeps being satisfied. So we basically want to say there is a classical uncertainty principle that fixes the entropy of each degree of freedom to be zero and not below. Then what we would expect is that you can't take, if you start with a distribution that has zero entropy on each side, therefore the determinant is bound, you can't make things go below. So that the Hamiltonian evolution keeps that bound satisfied.
Okay.
And so the idea should be like if you imagine the sort of you reduce the blocks to their determinants. What I expect to see is that you can take a sort of an uncertainty from 1 degree of freedom and move it, rotate it on the other side, or you can introduce correlations. So you introduce the correlation and then you're also increasing the uncertainties on each degree of freedom because again the volume, like the determinant of the whole thing is conserved because the total entropy is conserved. And so the only way that you can introduce uncertainty in each or sort of marginal entropy in each degree of freedom is if you're introducing correlation because now the sort of the volume remains the same, the entropy remains the same. So what I expect is that those sort of rotations and hyperbolic rotation that we see in the generator, they should do that. They should either like rotate the uncertainty, right? Or they introduce correlation. That's what I'd like to see. And I really think it should work, but we have to find the right expression. And then if we can, if we do find the right expression on the determinant, then what happens is that what I expect to happen, what I really want to happen, is that we are going to have some action on the determinants, right? So that the uncertainty goes around, and then some action within the block matrices that keep the determinants the same. So in the same way that we saw that happenings for the single degree of freedom, so each degree of freedom sort of always preserves the sort of the squeezing, the rotation of the boost within the degree of freedom, sort of only change the things inside and keep that determinant the same. I expect some stuff like that going to happen as well. So
Okay. We hope.
that's what I expect. Then we'll see if my intuition is correct or not. If it's correct, we have a nice result. If it's not, then
Yeah.
I learned something new. So
Yeah.
it's a win-win.
Okay. Okay. Thanks. Thanks for explanation because you know when I'm doing all those calculations, sometimes I just lose track
Of
of
the big picture, yes.
of the picture. So thanks for that. And okay, okay.
Yeah, you always have to go sort of back and forth. You start with a strong and big picture, then you do the detail, and then you figure out, oh well, I have to adapt my big picture because the details are not good, and so you go back up and down and so on.
Yeah.
So we do have a couple of questions. One from Julius: would Hamiltonians of warped tensor product would have any simple product here? I don't know what a warped tensor product is. It would count as interaction, but one subsystem might evolve independently and another would be influenced by the first one, or is warped product forbidden in this context? I don't know what a warped product is.
I don't know either. So it may be something to test, maybe.
No, it's if Julius joined in the room, he could have explained that. Like explaining it through the chat is not going to be so easy. Any other questions or comments? I'll give another 30 seconds and then we did the hour, so we can stop.
I have one um,
Go ahead.
observation, one could say. Mahad, Najim, could you show those squeeze, rotation, and boost matrices again?
Okay, no problem. I'm going to just share it. Okay. So preview. Okay. So only the element of the
Yes, on this.
okay.
This is just something that came to my mind. Maybe it doesn't mean anything, but squeeze, rotation, and boost matrices remind me about Pauli matrices. Have you noticed this before? The
Not
J1
really.
is exactly the same as the Pauli Z matrix. The rotation matrix is a minus I times the Pauli Y matrix, and boost matrix J3 is a minus 1 times Pauli X matrix.
Yeah.
Just wanted to bring this up
Yeah, yeah.
because
Yeah, you're right.
Pauli matrices have interesting properties. For
Mm,
example, there's one-to-one map from them to quaternions.
yeah. Maybe, hmm, maybe mm, I don't know because maybe the SP4R element may be some kind of Dirac matrix, for example. I don't know if we can use that. It's a nice remark, thank you. I didn't thought about that clearly, and I then you're right. It's exactly them with some factors missing, but hmm, maybe I should look at them in that way, maybe a little bit to see if we can re recover some of the results that we got at the end. But okay, thank you for that remark.
So at the end of the day, all these algebra are going to be similar because what's happening is that they're all linear groups. And the representation here, it's essentially the vector is two real elements. If you make them two complex elements, then you're going to get all the algebra of the 2 by 2 matrices that are complex, and the polymatrices are a subgroup of that, in the same way that these are a subgroup of that as well. And the thing that it would be more interesting to me is the real physical rotation would be when we have 3 degrees of freedom, right? And then the rotations are going to be again symplectic transformations. So there should be a generator inside. So once we get the sort of a three-dimensional, sorry, 3 degrees of freedom, three independent degrees of freedom, then there's going to be a rotation group somewhere there that is not just acting on the Q's, but it's also acting on the P's. And that would be the physical rotation that the polymatrices are going to represent. And then we also, as I said, was saying before, if we do this relativistically, now the way that this should be expanded relativistic is that you should have 3 degrees of freedom for space, and then 1 degree of freedom for time, where the conjugate variable is not energy but minus energy. And then some of these rotations become boost in space-time because you're rotating with the minus energy, and that minus is going to basically become a boost in space-time. And so those are also the other things that I'd like to see the connection to. Essentially, any linear group that we have in physics should be in some way expressed in some symplectic group. Because whenever we have these group transformation, either we are acting on states or like space-time variables, which are descriptor of the state anyway. Is just when we are looking at space-time transformation, we are assuming that the momentum change sort of covariantly, yes, covariantly, right? And so the transformation on space fixes the transformation in momentum, but then you still have a symplectic transformation. So that's why I really want to understand the symplectic group, and that's why I discuss this with Najim a lot. I don't understand why when you do special relativity or when you do quantum field theory, you talk about the Lorentz group and the Poisson groups, and then you have all these details about them, and you find the generators. And in most books of Hamiltonian mechanics, you don't discuss the Lie algebra, you don't discuss these things. And if you do that in this way, where you put all the position on one side and the momentum on the other side, that physically is not very useful. And I've never ever seen it done for the extended phase space, the phase space where you extend the position with time and energy. So, and I don't know why. It should be the obvious thing to do.
We may have to write a book on Hamiltonian mechanics only for that, just so people can see all the work on the symplectic group, because it's a really nice structure at the end. It's
Yeah.
to be able to describe all of the transformation that you can do on the center quantity of a theory, and for it not to be in some books is just, for me, it's too bad, you know.
Yeah.
It should be
And
otherwise.
I still suspect that some people has done these things, but it's it's in some obscure book somewhere or some article somewhere. The problem is that there is in some sense too much stuff done. A lot of things I I seem to have rediscovered a lot of stuff throughout the years, and some of them it's like I don't understand why it wasn't known. So I Yeah, anyway, I'll just shut up because otherwise I'll start ranting and I'll never stop. Julius has a comment. I wonder if you have enough structure to decompose the matrices into projection along the flow vector and to the substates perpendicular to that. Transverse and longitudinal part, and then study block decomposition and coupling of those things. I'm completely open to, as I said, like I don't know what is the right decomposition or the right way to look at this, right? We're basically start fighting around. I just have this intuition that the uncertainty should be doing something interesting and hopefully relatively simple. And I don't know how to take that intuition out yet. So. Okay, we did the hour.
No, maybe
Thank you
10.
everybody for joining. Thank you from Yajim for presenting. And again, hopefully this might inspire other people to collaborate and do stuff that is useful so that I can learn more things. And I don't think we have a topic settled yet for next week. And again, if somebody wants to propose something, please. And I'll see you next week. Bye, everybody.
Thank you. Bye.
Hi, Alex.